So in this video, we're going to do a quick review of the exponent rules from Algebra 1. And the first one we're going to look at is called the product rule. So the product rule is the rule you're going to apply when you're multiplying two bases that are the same. So for instance, here I have a to the x times a to the y. Well, so the bases are both a. So we can do this anytime that base is the same. And what the property says is when you have two bases that are the same that you're multiplying, you add the exponents. So for example, if I had x to the third times x to the sixth, that would be x to the ninth power. The quotient rule is the one we're going to apply when we're dividing two bases that are the same. So for instance, say I have x to the sixth divided by x to the fourth. So again, I'm dividing two bases that are both x. And this is like saying I have 6 x's on the top and 4 x's on the bottom. So it's basically like I can cancel all 4 of the x's on the bottom with 4 on top, and there's still 2 left over. So because 6 minus 4 is 2, so this would be x squared. So when you divide, you subtract the exponents. What about when you have one base and two powers, as we have here with the power rule? So if I have a to the x and then that's raised to the y power, what I have to do is multiply the exponents. So I'm going to multiply the exponents. So for instance, if I had x to the third to the fourth power, that would be x to the 12th power. And that's because it's basically saying I have 4 sets of x to the thirds that I'm multiplying together. So then I could go back and use the product rule. But this is a shortcut way, just knowing that if I have 4 sets of x to the third, then I have in each one of them multiplying 3 x's. There's a total of 12 x's I'm multiplying. And then the power of a product rule. So if I had a product, say I have x, y, so x times y, and I'm raising that to the third, that's like saying x to the third, y to the third. So we can simply distribute the exponent through when we have a product. We can also do that with a quotient. So a power of a fraction or a quotient rule would be like if I had x over y raised to the third, that would be x to the third over y to the third. And of course we can't simplify that because they're different bases. We just have to leave it like that. The zero exponent rule is kind of one that people get tripped up on. They often will say, I'll like say the statement, anything to the 0 power is, and then when people finish the statement, they always want to say 0, but it's actually 1. So anything except for 0 to the 0 power is 1. So if I had, say, z to the 0 power, it's just going to be 1. Just like if I had a to the 0 power, it's going to be 1. Or any number other than 0 to the first power. So if I had like 10,281 to the 0 power, it's going to equal 1. Okay. And then negative exponent. So a negative exponent rule is basically the negative means, it just means the negative exponent means take the reciprocal. And so it has nothing to do with the sign of your answer. So say I had something like 2 to the negative 3 power. Okay, that would really mean the same as 1 over 2 to the third, which is then 1/8. That applies to numbers, variables, whatever. So if the exponent is negative, it's saying take the reciprocal of that. Or alternatively, let's say you had a fraction, and say you had, 3/4 to the negative 2 power, that would be like saying flip that fraction and then square. So that would be 4 squared over 3 squared, which is 16/9. Now, the fractional exponent rule is a new one, so we're going to give it its absolute own slide, and we're going to talk about that next. Okay, so fractional, or what we often call rational exponents. So how does that work? So for instance, if I had something like x to the 1/3 power, that's a fractional exponent. So what does that mean? Well, what that actually means is this is a combination of two different things. One is a power, and the other is a root. So it's like we're combining two operations. We're taking a root of something and we're raising something to a power. Oops, my handwriting looks terrible. So what that really means is I'd be raising x to the first power, and then I'd have to take the cube root of it, or the third root, which is called the cube root. So that would look like this. It'd be x to the first, and then take the cube root of it. Now the x to the first really doesn't do anything to x, raising something to the first, right? So that's just like saying the cube root of x. So what would a normal square root look like? Well, a normal square root would look like, so this is what x to the 1/3 looks like. And then what about if I had x to the 1/2? Well, x to the 1/2 just means the x to the first and then take the second root, which really means square root. Okay? Now what about if there's a number other than 1 on the top? Well, then that means we actually have a power. So again, this means power. Higher power, right? I always think about it as like there's always a higher power. So the number on the top is the higher power, and then, or the power, and then roots grow below the ground, right? So I think about like, tree roots or plant roots or whatever, they're always underground. And so the denominator of this expression, this exponent, is actually telling us the root that we want to take. So there's two ways to write that. You could write it as the nth root of a raised to the m power, or you could write it as the nth root of a to the m power. So the exponent can either be outside the square root or inside. So for instance, say I put x to the 2/7. Okay, that would be like saying the 7th root of x squared, or the 7th root of x squared, and either one of them means the same thing. So it's just a way of doing two operations to a base at the same time, raising to a power and taking a root. And if the numerator is just 1, you're really just taking a root then. So that's just an exponential way to write a root, is to just say 1 over. So like the 4th root would be something to the 1/4 power, or the square root something to the 1/2 power, or something like that. So let's take a look at a few problems where we might go from one form to the other. So let's say I had something like the 5th root of x to the 2nd power. I could rewrite that in that other form as saying that's x to the 2/5 power. And that's because the top is the power, and the power that's on x is 2. And let's say I had something like, let's see, I'm going to go the 3rd root of x to the 6th power. So that would be, the power is on the top, so that's a 6, and the root is the 3. So that would be x to the 6/3, which then that reduces to x squared. That's actually going to give us some information about how we can simplify radicals later on. So if the power is divisible by the root, then we can take that's actually a perfect root then. So that would be like a perfect cube root. So let's go ahead and practice a few numeric ones. So what would 81 to the 5/4 mean? Okay, so remember the top is the power and the bottom is the root. Now because raising 81 to the 5th power, that'd be like a huge number. This is why I like to do the root first. So I could say that's the 4th root of 81, and then whatever I get, I'm going to raise it to the 5th power. Okay, so I could also write it like this. The 4th root of 81 to the 5th power. So I'm going to keep on kind of simplifying this down because it's the same problem, just gives me more places to simplify. So if I take the 4th root of 81, that actually, and if you want to use a calculator, there's you just have to use probably like something that looks like this, the x root of, and then you have to put 4 in. So when you put a 4, type of 4, and then type the x root of, and then it usually will just kind of go in and replace it depending on how updated your calculator is. Oops. This is saying take the 4th root of 81, which I happen to know is 3, So this really means 3 to the 5th power. Now, alternatively, if I wanted to do this one and simplify it, I have to take 81 and raise it to the 5th, which I definitely don't know that answer, and then take the 4th root of that huge number, which I definitely don't know. So I usually evaluate the root first. So then this really means 3 to the 5th power, so that's 3 multiplied by itself 5 times, which is actually, I think, 200, and it really means 3 times 3 times 3 times 3 times 3, which is, I think, 243. So that means the 4th root of 81 to the 5th is 243, or 81 to the 5/4 is actually 243. Now these answers don't always come out nice integer values. Like when we took the cube or the 4th root of 81, we got 3. If that hadn't happened, if this was not one of these perfect roots, then we may just not simplify it at all. We might just leave it in this form. But since this one's simplified, we went ahead and simplified it. Or if, let's say, the radicand was a variable, we wouldn't be able to actually take the root of it. So let's try a couple more real quick. So 625 to the 3/4 power really means the 4th power of 625 raised to the 3rd power. And again, or the other way around. So I could write it as the 4th power of 625 to the 3rd, which I usually will do if it's a variable, if I can't simplify it anyway, but so either way is fine. And then the 4th root of 625 is 5, and 5 to the 3rd equals 125, so this simplifies to 125. And maybe we'll look at one more. Let's look at this the one in the middle there. So this has got 2 roots. So this is, let me just kind of do this a little bit at a time. So this is the square root of, and then I'll interpret this one in underneath. So that's the cube root of 729x to the 12th power. So that's actually 729 to the 1/3 power. Okay, I'm just going to kind of leave these as fractional exponents. And then this is x to the 12/3. Okay. And then, so then if I simplify that, well, I can actually take the 729, and I think I can take the 3rd root of it. Let me just see if that's a perfect 3rd root or not. Oops. And that's actually 9. So that's 9. And then x to the 12/3 actually would reduce to x to the 4th. But now I have to square root these. So this is like saying the square root of 9 and then the square root of x to the 4th. Well, I can actually square root 9, that's 3. But how I would write the next part of it would be just x to the 4/2, which is like saying x squared. So this is kind of leading into one of the reasons why we're learning all this is so we can simplify something like this into something like this. So that's down the road a little bit. So for now, it's just really just being able to convert from one form to the other. So one real quick thing before we wrap up. So let's say we have something written like this, x to the 7/2. Okay. So then I know what that means is the root is a square root, right? So that would, because it's like a 2 root, I mean, you can put a 2 out there if you want, but we typically don't. It's just implied that if there's not an index on the root, that it means it is a square root, and then x to the 7. So here's what I'm saying is, what I usually do is if it's a variable like that, I'll just go ahead and put the power underneath because I don't have to really raise it to the 7th power anyway. Whereas, let's say we had something like this, x to the 2/7. If that's flipped, now that means the index is 7 and the power is 2. So the numerator, whatever it is the power that you're raising the radicand to, or the base to, and then the denominator is the root that you're taking. So that's just just some things with fractional exponents. Now, one last thing. So let's say we want to apply some of these rules, exponent rules, with fractional exponents. Say the power rule. So if we had, say, something like x to the 2/7 times x to the, let's see, 1/3. Now, normally, because they have the same base, I'd want to add those together. So I could rewrite this as x to the 2/7 plus 1/3.
right? Because we want to write it as a single base, we add the exponents. But because these don't have a common denominator, I would have to rewrite them so they have the same denominator. So the denominator would have to be 21, meaning I'd have to multiply the top and the bottom of this first one by 3, and I'd have to multiply the top and the bottom of this one by 7, and so then that really actually makes my exponents be, so 6/21, and then 7/21, which would then give me x to the 13/21. So once we have the common denominator, we just add the numerators, and then we reduce if we can, which we cannot. So you can really take these properties and kind of now apply them, but with fractional exponents. So the rules work exactly the same, but now we have fraction exponents instead of integers. So that does it for our little supplemental tutorial.